Test, test, test.
Test, 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 test.
Well, we will start next session soon. Please have a seat. Okay, thank you very much for joining us today. This is UNFCCC side event, new generation of greenhouse gas remote sensing satellite for contribution to the Paris Agreement. This event is co-hosted by National Institute for Environmental Studies, NIS, Japan, and University Space Research Association, USRA, in United States. And I'm Tsuneo Matsunaga from NIS, and I am in charge of the NIS GOSAT, GOSAT-2, and GOSAT-GW project. These are satellites for the greenhouse gas observation. And next to me is Dr. Tomohiro Oda, senior scientist at USRA and also adjunct professor of Department of Atmospheric and Oceanic Science, University of Maryland, US. And he is the founder of the famous ODIAC CO2 emission database. Could you have someone?
Hi, everyone.
Okay. And today, we too will chair this event. And we would like to thank UNFCCC for this side event opportunity. And before starting this event, I have some information for the participants on-site and online. You can watch live stream of this event by YouTube. And on-demand viewing via YouTube in a later day, it will be also available. And interactive online discussion will be held by Microsoft Teams, but it is limited to the pre-assigned participants only. And you can send comment to us by chat function of COP27 platform, but its availability depends on the situation of the network and the preparation of the secretariat. And also, we adapt the COP27's code of conduct. Okay. So I'd like to begin with, I would like to invite Mr. Hiroshi Ono, Ministry of Environment of Japan, for opening remarks. Mr. Ono graduated from University of Tokyo in 1987 and joined MOE. In the past, he served as the Director General of Environmental Management Bureau of MOE and Director General of Global Environmental Bureau.
Maybe we should try the old
Since
link.
2022, he serves as
Should we
Vice
try the old
Minister
link?
for Global Environment.
No, but we can ask this. I know
Mr.
something's
Ono,
coming.
please. University of
Oh, there we
Tokyo
go.
in 1987 and joined MOE. In the past, he served as the Director General of Environmental Management Bureau of MOE.
Introduction.
No, it's on now.
Good afternoon, everyone, and
You hear it? I don't hear
thank
it.
you very much all for participating in this event today, and thank the National Institute for Environmental Studies, NIS, and University's Space Research Association for your contribution to holding this event. In this event, we will introduce you the observation plans and expected outcomes of new generation greenhouse gas imaging satellites around the world, and discuss their possible contributions to the implementation of the Paris Agreement. The Ministry of the Environment Japan, Japan Aerospace Exploration Agency, or JAXA, and NIS launched the world's first greenhouse gas observation satellite, GOSAT, in 2009. Since then, we have continued observing GHGs on a global scale. For assessing and predicting the risk of climate change, it is important to estimate the global mean and geographical distribution of greenhouse gas concentrations. The GOSAT missions have contributed to understanding such overall GHG status globally, including the upper atmosphere and remote sites where ground observations cannot reach. Aiming at continuing our greenhouse gas observation missions of GOSAT and GOSAT-2, and further enhancing the observation capabilities. We are developing GOSAT-GW, which onboards advanced Tanso 3 sensor to be launched in next fiscal year in Japan. In addition to the measurement of the global mean and geographical distribution, it has recently become possible to identify large-scale GHG emission sources by GOSAT series satellite observations. The GOSAT-GW is expected to further improve the accuracy of such source measurements. I expect to have interesting discussions about how GHG satellite observations could contribute to the implementation of the Paris Agreement through international cooperation. Thank you very much.
Thank you very much, Mr. Ono, for very impressive opening remarks. Now, I would like to introduce today's speakers. We have 3 speakers today, other than me. The first speaker is myself, and the second speaker is Dr. Yasjka Meijer from European Space Agency. He's now online. Yasjka, would you wave your hand? Okay.
Hello.
And
Hope you can hear me.
he is a scientist for the Copernicus atmospheric mission, and he's the key person of the CO2 mission in the European community. And the third speaker is Dr. Annmarie Eldering. She is the president of the Eldering Consulting, and she is a former OCO3 project scientist, NASA Jet Propulsion Laboratory. And the fourth presentator is Dr. George Hurtt. Today he is online, and he is a professor, Department of Geographical Sciences, University of Maryland, US. And he is also a science team leader of NASA Carbon Monitoring System program. Okay. Now I'd like to show today's agenda. Just a minute. Would you go forward? Next, please. Next, please. Okay, thank you very much. Today, I'm sorry, the objective of this event is to showcase the advancement in space-based carbon observation, as well as emission monitoring capabilities expected from the next generation satellites, and discuss the use of Earth observation in driving actionable information to monitor and guide climate mitigation efforts in support of the Paris Agreement. And today, we will focus on the data from the new generation greenhouse gas satellites. And today we have the 2 presentations on-site and 2 presentations online. And then we will have the hybrid panel discussion. And the first 2 presentations will be given by myself and Dr. Yasjka Meijer from ESA. And my talk is supported by my Chinese colleague, Dr. Yi Liu from Chinese Academy of Science. And we will explain the next generation greenhouse gas observation satellite to be launched by Japan, China, and Europe in the mid-2020s. And after future satellite talks, Dr. Annmarie Eldering will show us the result of the NASA OCO2 and OCO3 instrument, including observation of plumes and cities. And Professor George Hurtt will share his experience in delivering satellite-based carbon monitoring products. And these 2 talks are very important in terms of converting satellite observation data into actionable information or application-ready product. And after the presentation, we will have the question and answer and the panel discussion. And please hold your questions until the end of the presentation session. And we may accept a question from the chat in a COP27 platform if network situation allows. And both of on-site and online participants can send a comment and question to us later via email. So I'd like to start my own presentation. Would you move? Okay. My talk is about next generation greenhouse gas satellite from Japan and China. And first, I'd like to explain about Japanese satellite. Would you go next slide? Okay, thank you. Okay. GOSAT series is a Japanese Earth observation satellite for greenhouse gas measurement from space. And we launched our first satellite for CO2 and methane measurement in 2009. This is GOSAT. And the second satellite, GOSAT-2, for CO2 and methane and carbon monoxide measurement, launched in 2018. And GOSAT and GOSAT-2 repeat point-by-point measurement globally, as shown in the upper middle picture of this slide. And we estimate vertical average concentration of CO2, methane, and carbon monoxide based on their absorption depth at a specific wavelength in the sunlight reflected at the Earth's surface, as shown in the upper right figure. And every month, would you go back? Okay, thank you. And every month, we obtain a global concentration map, as shown in the lower middle in this slide, lower middle figures. And in addition, from such monthly data for more than 13 years, we can obtain the long-term trend of CO2 and methane, as shown in the lower right of this slide. And we will launch the third satellite called GOSAT-GW with a newly developed imaging spectrometer in the fiscal year of 2023. Would you go next slide, please? Here, this slide shows the timeline related to IPCC, UNF, CCC, and GOSAT series. We launched the first satellite in 2009 and operating it for more than 13 years. During that time period, IPCC published 2 reports, AR5 and AR6. And as you know, now climate crisis is gaining more social attention than ever. And under the Paris Agreement adopted in 2015, global stock take will take place every 5 years, starting from 2023. The time frame of the first, second, and third global stock take is fitted very well to the operation period of GOSAT series. That is, we are providing GOSAT data for more than 13 years to the first global stock take in the next year. And we will provide GOSAT series data for more than 20 years to the third global stock take in 2033. Next, please. And based on the current situation of the Earth's climate and related international and domestic policies, Ministry of the Environment of Japan decided the mission objective of our third satellite, GOSAT-GW, as shown in this slide. First, monitoring of whole atmosphere global mean concentrations of GHGs. Second, verification of national or country-specific anthropogenic emission inventory of greenhouse gas. Third, detection of greenhouse gas emissions from large emission sources, such as megacities, power plants, and permafrost. And the GOSAT-GW specifications shown in the next slide were determined to satisfy these objectives. Next, please. Here I summarize the specification of our 3 satellites, GOSAT, GOSAT-2, and GOSAT-GW. And GOSAT and GOSAT-2 are making a point-by-point measurement as shown in the second picture from the left, using a Fourier transform spectrometer with very agile or flexible pointing system. But GOSAT-GW will do imaging of greenhouse gas with 2 different spatial modes, wide mode and focus mode. So by GOSAT-GW, we can both global monitoring and regional mapping of greenhouse gases frequently. And in addition, we will launch GOSAT-GW in fiscal year of 2023 to avoid the gap of the data, as design lifetime of the GOSAT-2 will end in the fiscal year of 2023. And the lifetime of the GOSAT-GW is 7 years. This is longer than previous satellite, and this is to secure longer provision of the observation data from space. And we will also measure NO2, nitrogen dioxide, a good tracer for fossil fuel use. Next, please. And the most important feature of GOSAT-GW is its spatial observation or imaging capability of greenhouse gases. It has two modes, a wide mode with 900 kilometer swath and 10 kilometer resolution, and a focus mode with 90 kilometer swath and 3 kilometer or higher resolution. And by wide mode, we can obtain a frequent global coverages of CO2, methane, and NO2. And by focus mode, we can monitor regional emission from urban areas. And as I shown in this slide, we designed the focus mode to observe Tokyo area in one shot. And we will provide such GOSAT-GW data from 2024 to 2030, and hopefully beyond, to the global community. Next slide, please. I would like to move on to the Chinese satellite. This slide and the next slide were given by Dr. Yi Liu of Chinese Academy of Science to explain the Chinese next generation satellite. As you may know, China have launched several greenhouse gas satellites in the past decade, such as TANSAT launched in 2016. And based on experiences obtained from these satellites, several options for next generation satellites which satisfy science objectives were investigated, such as the low Earth orbit satellite shown in the lower left of this slide, or middle Earth orbit satellite shown in the upper right of this slide. Next, please. And based on the investigation shown in the previous slide, the measurement requirement of the future satellite called TANSAT-2 was determined as shown in this slide. And what I think most important is one-day global coverage realized by 3 satellites. And each satellite will carry a large swath spectrometer as large as 800 to 1,000 kilometers, which is similar to GOSAT-GW. And its pixel size will be 2 by 2 kilometers at nadir. This number is similar to European CO2M. And the measurement target are CO2, methane, NO2, carbon monoxide, and solar-induced fluorescence. And I understand the eventual objective of TANSAT-2 are similar to GOSAT-GW or CO2M, but it will realize the objective in a different manner. Okay, that's all my talk. Thank you very much for your attention. Okay, let's move on to the next talk. Next talk is an online talk given by Dr. Yasjka Meijer from European Space Agency. She will talk about European CO2M mission.
Good afternoon, everybody. Can you hear my audio?
Yasjka, you can start.
Okay, thank you. Thanks for giving me the opportunity to present this satellite mission. So the title is Copernicus Satellite Mission for Monitoring Greenhouse Gases. So this satellite mission is implemented.
I can't hear you.
Their audio is not coming, or you cannot hear anything? Can you hear me? Can other people in Teams hear me?
I can hear you in Teams, yeah.
Yes, now I can hear you. Please start your talk.
Okay. Thanks for giving me the opportunity to talk and present this satellite mission that's being developed in the framework of Copernicus. And it's aiming for monitoring greenhouse gases, but specifically for anthropogenic greenhouse gases. I'm Yasjka Meijer and I work at the European Space Agency. Next slide. So what we are developing is an overall system. So we are really aiming to set up a system from the beginning to monitor and verify anthropogenic emissions from both CO2 and methane. And it will be developed as a support capacity. It's not replacing, it's really complementary in support. And it consists of a number of pillars of observations, of which satellite observations will be one of the main contributors. There's a lot of prior information needed in order to use this kind of data. And then a whole modeling and integration system in order to understand and attribute the observations and come with the output at different levels. So there's output at country and regional level, but also at the more local level of, let's say, hotspots from power plants and cities. And these are all leading into what we call actionable information. So it really aims all the way up to the policymaker to provide useful data. And it's really exciting to see this being developed all in coherence at the same time. And we're doing this with partners at the European Commission, ECMWF, and UMETSAT. Next slide. The overarching system requirements that they have been giving is that we will be detecting emitting hotspots. So that's megacities and power plants. But besides from detecting them, we really want to quantify their emissions and then monitor these over time. So this is what we call the monitoring of these hotspot emissions. And then at a little bit larger spatial scale, we want to assess the emission changes against local reduction targets. So we're talking about then more the national scale and then also to contribute to the nationally determined contributions. And then at a bit longer time scale, we also would like to support changes over the larger scale and contribute to the global stocktake. Obviously, this is a system that would be operational, and while maybe there are 5 yearly global stocktakes, we can produce data on a very regular basis. And the basis for all these requirements are in these reports from the European Commission. Next slide. So in order to design such a system, we need to have several measurements. To measure CO2, as you can see in the simulation on the top left, with a swath width of 250 kilometers that we're targeting, emissions from power plants, in this case it's in Germany, in the Berlin area and some power plants to the east. It's very difficult to see the emissions on top of the very huge background, and the background is also varying a lot. So we are having a, let's say, assistance here from measuring also NO2, because NO2 is co-emitted in high temperature combustion processes, and it gives a telltale to where the plumes of cities and power plants are, and then helps us to reduce the emission uncertainties and really come with a proper estimate of the emissions. So the slide on the photo on the right, you can see that we have multiple instruments. So one is actually viewing forward and backward, and that's really needed to reduce the errors that are otherwise introduced by aerosol that's in the same area. Next slide. So to be pretty concise here, just to report the products. So we are aiming to have a precision of 0.7 ppm for CO2. You should realize that the background concentration is now well over 415. So you're really talking about less than 0.25% of precision, which is extremely difficult to achieve. But this is what we are currently developing. The CO2 bias, which is otherwise really disturbing your interpretation of the data, we need to maintain this to well below of 0.5 ppm. And this is why we needed these aerosol measurements that I was alluding to before. We're also in the same wavelength range measuring methane. So we will be able to measure methane at the same spatial resolution across the same swath with about a precision of 10 ppb. NO2 is what we need to find the plumes, same spatial resolution, same area. So we are looking at 4 square kilometers and a 250 kilometer swath. The satellite will be flying close to local noon at a 735 kilometer altitude. We're aiming for a constellation of satellites. We have the funding for 2 satellites that are currently being implemented, and they will be delivered to us in January 2026 that allow a forecasted launch in early 2026. We're still discussing with the European Commission to get the funding for a 3rd satellite. So in theory, the constellation should consist of 3 satellites. The nice thing about Copernicus is that the data is fully free, available on a non-restricted open basis. I'm not sure if you're able to start the video animation. If not, we just go to the next slide. Yeah, yes. So this is showing you the coverage with a 250 kilometer swath, and then we add the 2 and a 3rd satellite. And this is really the kind of coverage that you would get during a day. And you can see the underlying CO2 fields that you can measure. The satellites will have 2 different modes because over water, the reflection is pretty poor. So we have to point towards the sun glint. So to also get good measurements over water and also over snow-covered regions. You can go to the next slide. I think the nice thing is that we are developing all of this in conjunction with the colleagues that we are currently in the room. So we are collaborating to set up a full measurement system. And also on this note, we have been advising the White House to also come up with an American system and improving the measurements of greenhouse gases emissions. And with that, I would like to conclude. Thank you.
Thank you very much, Yasjka. Thank you very much for your great talk, and I'm happy that CO2 emission is progressing very well, and I hope you will have enough funding for the 3rd satellite in the future. And the next
Thank you,
talk,
yes.
Okay. Next talk will be given by Annmarie Eldering-san.
Right, so I'm going to provide a brief introduction to Annmarie. Dr. Annmarie Eldering has over 30 years of experience in the fields of atmospheric pollution, greenhouse gas, also remote sensing. As previously mentioned, that she recently retired from the NASA Jet Propulsion Lab and just last year, and he's now president of the Eldering Consulting. Congratulations. As JPL, she has been the project scientist for the OCO3 emission, and through this project, she has been closely working with the modeling community and combining those information and studying carbon cycle. So now, Annmarie, take it away.
All right, thank you, Tom. Hi, everybody. Glad to be here. And you heard 2 great talks about some of our satellites of the future. And what I'd like to do today is share with you some information that we've actually gathered, a little bit of information about where we are with our goal of trying to gather more details with space-borne measurements. So if we can go to the next slide, please. So we have many measurements that are already being gathered. And satellites are really an important asset in this whole network of information, right? This is a model field of carbon dioxide. The brighter spots are where our ground-based measurements are. But as you can imagine, with satellites, you start to get a deeper picture of the world, southern hemisphere, over the oceans, in these regions we just didn't see before. So if we go to the next slide, but it's certainly a challenge for us. We have made a lot of progress. I joined the OCO program in 2010, shortly after the GOSAT satellite had launched. And in that time, we've definitely demonstrated this capability to measure carbon dioxide from space. I'll talk a little bit more about how precisely we can do that, but it is fair to say many of the early measurements were rather sparse networks of data, not global coverage. And methane is similar. We're advancing our capabilities. The GOSAT instrument was early mapper. We had large footprints with other Skiamaki and other data sets. And now we're moving to a new finer scale in methane measurements, and I'll describe that a bit. But we face this challenge, right? We're here at COP27. We're not all about science. We're about action, policy. So how do we turn these satellite data into information that can be used in the policy arena? The next slide. Just to remind you, 1 in 400 is what we're aiming for with some of our first goals on carbon dioxide. Here's 400 dots. We go to the next slide. I've added one more. We'll see if you can see it. And then highlighted it in gold. So we're really looking for a very small change in carbon dioxide. So that was a real challenge to do this from space. If you could advance. Fortunately, when you're over the cities, go ahead one more, those enhancements are larger, right? Large emission sources, we maybe have 5 part per million enhancement. That's a little bit easier for us to pull out. So we go to the next slide. The OCO2 instrument, which I was very heavily involved with, managed to show against the validation network that we have a bias of less than 0.3 part per million with an RMS about 0.85. So you saw that 1 in 400. You heard Yasjka talk about 0.7. These are difficult requirements, but they are achievable, we believe. If you go to the next slide, you'll see that these big natural cycles, the breathing of the Earth, are very visible in these remote sensing data. These are just snapshots from springtime and then early summer, where you see the northern hemisphere trees and plants are becoming active and they drastically reduce the carbon dioxide. So these big cycles, we can see the growth of 2 to 3 part per million per year is very obvious in the data. But again, what about something you can use in your policy planning? So the next slide, I've got a couple of examples here. Los Angeles is sampled on the right-hand side with some of the early OCO2 measurements. This is about 10-kilometer wide swath of data, 2 kilometer by 2 kilometer. You can see the southern part, which is the urbanized area of Los Angeles, is warmer colors, higher concentrations than the desert north of the city by about 5-6 parts per million. On the left is a new innovation. This is Jana Hakkarainen's work, where the tropomi NO2 field is shown in the more map-like data, a red triangle on an emission source, and you see that yellow plume heading to the left. That's the nitrogen dioxide plume. OCO2 with its narrow swath just cuts through from the bottom to the top. The carbon dioxide's also high. You can see that red where the two measurements are intersecting. So when we use the NO2 and the CO2, we start to even understand more about these emission sources. And this is with real data we have in our hands today. On the next slide, you'll see some additional examples. If you could maybe click and make this animation run. With OCO3, a new instrument put on the space station in 2019, we actually, there's a video in the next slide. Oh, maybe it's a PDF. This video may not show. Check out our website. We can map out 2 by 2 kilometers. An 80 by 80 kilometer area is measured in 2 minutes. And I'm sorry this movie didn't work. But this would show you that over Los Angeles now with OCO3, you actually map out the whole city instead of just a swath. And we can see these variations of carbon dioxide along with additional NO2 data from tropomi. So OCO3 was a new step forward. And on the next figure, next slide, we have Belcatau is a power plant that we visited 8 times in a year and a half. And so we could see these plumes from the power plant. Each visit looked a little different because of the winds and the emissions. On the right-hand side, you see work from Ray Nasser and his team where they've tried to turn OCO3 observations of carbon dioxide into power plant emission estimates. So the red line with the uncertainty is the estimate based on the satellite, and the blue is reported by the power plant. So we did this where we knew the emissions to really understand if the method works or not, and you can see that we can largely reproduce reported emissions within the uncertainties. So again, the utilization of more of a mapping framework like you heard about for these next generation instruments has shown power in trying to get down to source level quantification. On the next slide, just looking at cities as an aggregate, again with OCO2 and OCO3, Chevalier et al. Analyzed the cities, and if you look on the right-hand figures, these are comparisons of bottom-up and observations. This is a log scale, so there's a very wide variation still. Chevalier thinks there's some skill in looking at cities with these instruments. I think we're still need a larger, deeper set of data like we'll see collected in the next generation. So the cities, in my mind, are still a little bit at the edge of what we could do. And now I think on the next slide, I want to dive into methane for just a moment. So methane is a different beast than carbon dioxide. The enhancements when you have a plume are 10% to double the background, so it's an easier change to find. A lot of work had been done with aircraft data. These are two cases that were studied with aircraft over oil and gas emissions. And on the right-hand side, you see the methane enhancement where there's about a doubling from the background. So this has been demonstrated with aircraft, and now if you go to the next slide, you'll see some of the instrumentation that's doing this. You probably have heard about GOSAT, which is a different technology, but TROPOMI and EMIT are other instruments that can see these methane enhancements. TROPOMI is information on a large scale. This scale of this image is a plume of over 100 kilometers. But EMIT on the left-hand side was newly installed on the space station. It's focused on mineralogy, but you can find methane plumes with this instrument. And so you see here just a few kilometer long plume, again, doubling a background over an oil and a gas region in the US. So we're starting to see a lot more different focused methane measurements over source areas. Next slide. So have we reached this actionable data at relevant scales? I think I've tried to demonstrate we can quantify carbon dioxide at power plants. City scale enhancements are still highly uncertain, but localized methane plumes are starting to now be studied with our various instrumentation. So where do we need to go? If you go to the next slide, we need more information, and I think what Yasjka described, what we heard about from the GOSAT and the NICE and the Dr. Liu, it's not just a single measurement. It's an integration of information. We need spatially resolved data. We need a variety of emission information. The carbon dioxide, the NO2, even SO2 can be useful. Activity data. You probably heard about Climate Trace earlier this week. It's a great approach to try to bring new information on what the activities are and integrate that. And this is where I think this collaboration, you heard from scientists across the globe, we tend to really work together with carbon dioxide, methane, and other trace gases. We need to build integrated tools that are bringing measurement data, atmospheric understanding, bottom up, and put those pieces all together. So I think we're on the cusp of, we're already exciting new information, but it's going to get even better with the next generation of instrumentation and tools that we plan to build. And I believe that's the last slide. Oh, just remind you already heard about all of this, the next generation of instrumentation. Carbon mappers, another one I wanted to mention here, which is like EMIT, but a smaller ground footprint that will be focused on oil and gas, ag, landfill emissions. And next slide is the last one. So I think I already said all of this verbally, but I think we're heading in a great direction, and thank you for listening to my portion today. Thanks.
Thank you, Annmarie. So I'm going to introduce the next speaker, to Professor George Hurtt. George is a professor at Associate Chair in the Department of Geographical Sciences at the University of Maryland, College Park in the US. George Hurtt studies the impacts of the land use change on the climate. He has been contributing author to the IPCC AR5W Working Group 1 report. George has been involved in many research projects such as North American Carbon Program, the US Department of Energy Exascale Earth Modeling System Modeling, and also US EarthCube. Also most importantly, NASA's carbon monitoring system, which he'll be talking about. George is on travel this week, but he graciously agreed to speak for us. So thank you for being with us, George. Floor is yours.
Okay, thank you very much. I hope you can hear me. Is that correct?
Yeah, loud and clear.
Very good, thank you. So I'll be talking today about how the NASA carbon monitoring system has developed application-ready products to support stakeholders. Next slide, please. The NASA carbon monitoring system was initiated in 2010. Its goal is to develop the prototype capabilities necessary to support stakeholder needs for the monitoring, reporting, and verification of carbon stocks and fluxes. It has comprised of over 100 projects to date, operating in every major sphere of the Earth system: land, ocean, atmosphere, and the exchanges between these spheres. Next slide, please. NASA's approach to carbon monitoring and MRV recognizes that a sustained and observationally driven system using remote sensing data has the potential to significantly improve the relevant information base for the United States and the world. It recognizes that there are multiple users, multiple scales, multiple quantities of interest, multiple frameworks for MRV, international, national, subnational, and even carbon markets. It recognizes the importance that user engagement plays to be responsive to stakeholder needs. Next slide. To date, NASA CMS has developed over 130 different products. 37 of those products are global in domain and not shown in this slide, but the remainder have regional or even local focus. You can see a high concentration of focus over North America, the United States in particular, also South America. We also have projects operating at more local scales around the world. You can see some of those. The reason for those local scale products is to develop the fine scale, bottom-up, accurate capabilities needed for later global application. Next slide. The time domain of these products is focused predominantly on the 2000 to 2020 time domain, as you can see in this chart. However, we have several projects that extend back further in time, trying to get to the policy base year of different stakeholders, and other projects that actually project forward in time, trying to inform the planning that many of these stakeholders have. Next slide. CMS has developed several major success stories. I'm going to just give you a brief introduction to some of those. The CMS has used LiDAR remote sensing and high-resolution optical remote sensing to implement the first remote sensing-based forest carbon monitoring system in official use by a United State of Maryland. So this is the first state to officially use a remote sensing-based forest carbon monitoring system. CMS has partnered with the United States Forest Service to do forest monitoring in the interior parts of Alaska, which is very difficult to access with traditional ground-based methods. CMS has partnered with the U.S. Environmental Protection Agency to spatially grid the emissions of methane to 0.1 degree resolution, something previously not accessible from US EPA data. Next slide. CMS also operates over the ocean, and they partnered with, here illustrating the Gulf of Maine time series, Gulf of Maine time series activity, which conducts transects of ocean carbon properties, but CMS has partnered with them to link satellite data over the ocean to spatially extend those products over the ocean. They've partnered with the government of Indonesia to develop official estimates of carbon emissions from fires from peatland. And finally, as an example, they've partnered with the NASA GEOS-5 team to include carbon in the global atmospheric model GEOS-5. Next slide. So NASA does this not by itself, but with participants, and this is actually critical to its success. So far, NASA has engaged over 700 participants in the development of these products. You can see that the majority of these are US-based participants, but even within the US, they come from a variety of different organizational types: universities, federal agency, state agency, local agency, companies, NGOs, research institutes, and others. We've also partnered internationally with scientists from different countries shown in this slide. Next chart. So this is really the essence of the NASA CMS approach, is a very close partnership between scientists and stakeholders. We strive for an end-to-end full product cycle partnership where stakeholders are involved even in the design of these products. And this ensures that the products that are developed have maximal relevance to stakeholders when they're complete. Together with these project-by-project relationships, we have a systematic applications approach which enhances and coordinates all the various stakeholder scientist partnerships we have, illustrated with some of those activities on the right. Next slide. All right, so in conclusion, NASA carbon monitoring system has produced one of the largest collections of applied carbon monitoring products to date. Key to this effort has been the exploitation of remote sensing and modeling expertise, collaboration with scientists, and data products from other agencies, and the end-to-end focus on stakeholder engagement to meet stakeholder needs. In fact, we've done research on this, and the scientist-stakeholder relationships actually drive the carbon data product transfer effectiveness that we have within the NASA program. If you'd like to learn more about NASA CMS, you can follow this website, carbon.nasa.gov. Thank you very much.
Thank you very much, George. Your talk is very great, and NASA's carbon management system is one of our future view of the new system, which will use the next generation greenhouse gas satellite in the mid-2020s or later. Thank you very much. Now we finished the 2 future satellite talk and 2 application talks. And now let's move on to the panel discussion. From now on, Dr. Tomohiro Oda will chair this session.
Right. Thank you, Matsunaga-san. So we're moving on to the panel discussions. We're going to invite 2 more people on the podium, actually one virtual. The first one is Akihiko, Dr. Akihiko Ito. He's the head of the biological chemistry, chemical cycle modeling analysis section at the National Institute of Environmental Studies. And also one more is DeCola-san on virtual. So he is the co-chair of the WMO Integrated Global Greenhouse Gas Information System, IGES, Science Theory Committee. And also he is adjunct faculty at University of Maryland. Also, she's the Chief Science Officer of GIST Earth at Washington, D.C. Thank you, DeCola-san, for calling in. And before getting into the panel discussion, we'd like to take a couple of questions if you have anything from the audience. Yeah, participant in the middle. Yeah. Oh. Could you microphone, please? Also, could you identify yourself?
I'm Nancy Sherman with the Institute for Governance and Sustainable Development in the U.S. I have a question for Dr. Is it Meijer? I'm sorry if I'm mispronouncing that. I know you're in the data collection and analysis end of the field, but I was curious about a couple of your slides that showed large amounts of carbon dioxide across the oceans, the Pacific and the Atlantic, in sort of a belt. And I was wondering if that's just atmospheric effects, or if you happen to know what that's from. Could it be from forest fires in Southeast Asia or South America? And I'm not even sure that that's what the slide was showing. But can you speak to that? Thank you.
I can comment a little bit on this. Yeah. Well, there's a lot of, let's say, carbon weather. So the carbon is fluctuating a lot by all kind of biogenic influences. And then whatever is also introduced by anthropogenic emissions is then affected by all kind of weather systems all around the world. So you will see a mix of different effects from that can be forest fires, it can be even biogenic uptake, or kind of effects. And I think maybe my colleague George can even comment better on it because he's more on the data interpretation side of it. George, you want to comment?
Sorry, no, I don't have anything to add to that particular question.
Okay, thanks. I hope that addressed your question.
Any other questions? Yes, participant in the front.
Hi, this is Sami Izutu from Sumitomo Corporation. Thank you for the presentation. I have a question to Dr. George Hurtt. According to your slide in the presentation, CMS participants include some companies, but could you explain the purpose, some example of the purpose, about the purpose of the companies? Because are they only for the carbon markets, or if there are another purpose to use the satellite CMS? Thank you.
Thank you very much for the question. The question's about the companies participating in CMS. And thus far, the influence of companies has been primarily, yes, focused on carbon markets and also on the development of technologies related to remote sensing as well. So I would say on the technical and carbon market side. But I think in the future, we aspire to engage companies more broadly. Thank you.
Thank you for your questions. So this is already leading into our topic of panel discussion today. So we want to discuss, we have seen lots of new satellites coming in, also existing one. We are trying to convert those information into actionable information. This is our core of the discussion today. So let me start with asking Ito-san. You are leading Japanese project so-called S28. Would you happy to add some example from your project?
Hello everyone. My name is Akihiko Ito, researcher of National Institute for Environmental Studies Japan. I'm working on some biogeochemical modeling of terrestrial ecosystems, and I'm a project leader of S28 project. That is a project funded by the Ministry of Environment. This project aims at contribution to the global stocktake by providing the greenhouse gas budget from an integrated manner using not only satellite but also field measurement data. Today, I enjoyed the talk by the outstanding researchers for the recent progress in satellite remote sensing on greenhouse gas budget. And especially, I was impressed by CMS by United States because this is a very extensive project to monitor the carbon budget in United States. I was particularly impressed that this project evaluates not only flux but also biomass, that is the stock of carbon. In our project, we focus on the flux of carbon dioxide methane, but we cannot focus on the stock of the carbon because this kind of variables need another observations, such as GOSAT and TANSAT OCO provide the concentration and flux, but to evaluate the stock, we need another facilitate, such as a LiDAR or synthetic aperture radar. So we need more integrated use of the satellite data to measure both flux and biomass. That's all. Thank you.
Thank you, Ito-san. Yeah, integration is the key. Phil, could you share your sort of experience with the IGES project? You have lots of the application cases.
Thank you very much, Tom. Can you hear me?
Yep, loud and clear.
Wonderful. And thanks to all the presenters. I agree with Ito-san that this was a wonderful session so far with really exciting description of all the activities out there and the planned and current missions. I wanted to give some background on the two greenhouse gas initiatives of the World Meteorological Organization. There's a new one that's just getting underway and is in its concept study phase, which is the Greenhouse Gas Infrastructure Initiative. And that one is very much in line with a lot of the work you've heard so far. It's looking at how can we go from all of these beautiful demonstrations of the use of satellite data in the context of a multi-tiered observing system and fill the gaps and to really flood the zone with all the necessary data that we need to really serve a variety of stakeholders in so many different climate action arenas. The other one is one that's been going for a while now. It's beyond its concept phase and has been actually started back at the time of the Paris Agreement in 2015 for COP21, and that's the Integrated Global Greenhouse Gas Information System. And it's not about infrastructure, it's really about this word that we've all used about actionable information. And in that sense, what we're really doing is trying to get down into the trenches with users and to co-design, not just to throw data over the transom and hope that it gets used effectively, but to sit around the table with the stakeholders, with the users, understand their needs, and then find the very powerful data and research and development tools that we've developed in the research realm and translate that to the specific needs of the users. It's very hard work, and it requires very busy scientists to take a little time away from, you know, the pushing the frontier of knowledge forward, to sit and to go out and meet with the users. And that's what this science for services is really what the IG3IS, which is the acronym for the Integrated Global Greenhouse Gas Information System that we use, IGUS. And so I think that I just wanted to, you know, emphasize that it's very important that we as scientists take that time to sit around. And then one other point is that this is a hybrid approach, so that we're not trying to, in the sense, verify what the classical activity-based data, emission factor-based inventories, but we want to work together with those who have been working hard at that over the years now to create a hybrid approach where we take the top-down information from satellites, aircraft, and tower measurements and the model analysis and combine it with increasingly powerful granular statistical information from the bottom up to create the best possible information to target the low-hanging fruit opportunities to reduce emissions, and then to track the efficacy of those policy measures over time.
Thank you, Phil. So mostly our session focuses on the use of satellite remote sensing, but that's not the only data set we can get as our observation. They feel particularly taking the data set from ground-based measurement, that's also the variable asset for us. Then integration is really key for producing actionable information. So I want to ask more about, because we really have to communicate with our stakeholders, and we do science, they produce useful information, but sounds like the people already identify some challenge and difficulty when communicating with people. And I want to challenge our panelists, then sharing some of the already identified challenge, difficulty, then how we can move forward into the future. Who wanted to pick up? Since Annmarie, you're next to me, so sorry.
Okay. Yeah, thanks, Tom. I'll make a few comments, and maybe we should get Yasjka in on this. So this question of how do we make data that's useful to the end user, how do we connect with the end user, I think has really been a sticking point for a lot of the development work. And I think Yasjka can speak to the services they're building. And a different example is one we're seeing designed within the Carbon Mapper project, and also related to what you may have heard from the UN's Methane Emissions Observatory. And there the idea is that you make measurements in a very focused way to find methane plumes. You have a database of who all the owners are of various equipment, landfills, ag facilities, oil and gas, and then you actually try to communicate directly to the end user when you see something anomalous in their region. So conceptually, it's easy for me to say that, practically to implement that, keep it up to date when there's continual development, new sources, closing down of old sources is tricky to do, but that's an approach we're trying to get implemented, and Carbon Mapper wants to bring online end of the year, end of next year.
Thanks, Annmarie. So George?
Yeah, thank you. I think the most important strategy for communicating with the stakeholders, I think, is the long-term sort of co-production approach, as opposed to, I think, as Phil was saying, throw science products over the fence. This long-term co-production is so important because in many cases we need to get the terminology consistent between stakeholders and scientists. We need to develop trust that these science products are going to be mature and sustained over time. We also need to be clear on what the variables of interest are. Sometimes for stakeholders, the variables of interest are somewhat or even quite different than what the science products are producing. So I think for all those sort of more nuanced reasons, this long-term sort of co-production is the most important strategy. Thank you.
Yep. Now Phil?
Thank you, Tom, and thanks, George, for emphasizing that point of the co-design, co-production. And you used the word trust. I wanted to amplify a little bit on that. You know, we've had skill in the measurement-based, observation-based research realm for a long time now, going back to even before the Paris Agreement. And I think one of the problems is that we may have been overambitious in our original attempt to work with stakeholders. For example, one of the big stakeholders that we've mentioned are the inventory compilers from nations who have been working, so hard over years to help their home nation report on their emissions to the Framework Convention. And I think in some cases, when we've come along and said we're going to use our atmospheric measurements to verify the emissions and fluxes, I think there's been some confusion there. And really, I think we need to build trust and a working relationship. And it just really requires, understanding each other, as George was saying, the terminologies, and making sure that we're not talking past each other. And that takes time. It's relationship building, really. And now we've started to see more countries around the world where their inventory compilers are working with the atmospheric scientists and the carbon cycle scientists, and starting to see great value from combining these layers of information into an a posterior, much more granular and more accurate and precise set of information that can guide climate action. So it's that trust, and it takes time, and it takes, building those relationships and understanding each other, as George was saying.
Yeah, thank you, Phil. So just before this seminar event, we had a WMO event where we should be discussing inventory compilers and also science researchers, and especially at 2019 refinement, the use of atmospheric measurements are recognized. So this is a time for communication, the building up that integrated system to contribute into the climate action. Yasjka?
Yeah, I would like to add on to that. So I think it's really highlighting what Phil is saying, is that we need to build the trust, and that's also why we call our system support capacity. So it's really to add on, it's not to replace. It's to add to the transparency framework that was stipulated also in the Paris Agreement. And also the nice thing about satellite observations is that there are no borders. So the system will measure the same thing all around the world. So you can compare one country with another. And the other very great thing, I think, of this kind of observations and building a system is that you can get very timely information. So if you want to have actionable information, you need to know now what's going on. And a lot of the inventories, some of the inventories, I'm not saying all of them, but some of them, they come like years after the actual year of emission, and that's not actionable for policymakers. So this is really to help and support the whole process, and I hope that people will see this value. I think for methane, we have seen very recent examples that are very supportive in being able to take action. Emissions from landfills from all around the world, specific hotspots that were not known. And people are challenged then, people are challenging their local policymakers. Why is there so much methane coming out of the landfill? And you get discussions. And I think this is the great thing about Earth observation, is that you can create such discussions and move forward.
Thank you, Yasjka. Now, Matsunaga-san.
Thank you very much for comment, George and Phil. And the long-term co-production, like George said, or the communication with the inventory developers, like Phil said, such is a very, I think these are very important issues. But in such case, it is required to provide long-term data or global data or consistent data to the community. And in our community, in the satellite observation community, from the point of view of research and the development, new satellite with new instrument is very fancy and attractive. And we'd like to have such satellite again and again. But if we think about collaboration with the stakeholders, we should be careful about provision of the data, global, consistent, calibrated, validated data set. That's my comment. Thank you.
Right. Thank you, Matsunaga-san. Yeah. So sounds like they already identified the challenge, but communication, also building trust is a key for the next step. There's still a gap between what we can provide science and also what actionable the state subnational actor might be demanding, but it sounds like we are filling a gap, and hopefully the new satellites going to measure lots of different variables and help us to close the gap one or more, then help out the climate action. So right. So actually, we have to go to the closing. Time is limited, so we have to close the session. So could you advance the slides one more? So just trying to summarize discussions. So like I mentioned, in this decade, new generation satellites, great. It's coming out. Yes, so new generation greenhouse gas observing satellites such as GOSAT-GW, CO2M, also China Tansat, will be implemented global and frequent observation with focus on, especially on emission monitoring. And the data collected for those satellites should be a tremendous opportunity. They provide an opportunity for developing actionable and applicable information, especially for subnational actors. And also those information should be used by not just the parties, but also, like mentioned, is the state government or NGOs, businesses, all the actors. Based on what we're hearing from today's discussion, is pretty promising. And it looks like we need some system to developing the data, also implementing those data production or future. So this is actually happening in the US, Europe, Japan, as you see, as you hear from the speakers. And last of all, the situation has been clear that it's happening, climate change is happening, that we need to act now, especially this is the implementation COP. So we have been prepared for us to guide us to reach the Paris Agreement goal, and we have to continue communicating for a better future. So with that, I wanted to close this session. Then first of all, I'd like to thank all of you participating here, also participating in the virtual audience. Also, I totally forget to mention this, but I would like to thank all the speakers first.
Arigato.
Thank you so much. Again, thank you for being here with us, and I hope you enjoy the event. As just a note, we have another event after this at Japanese Pavilion from 5:15. Hope we see many of you there too. And I think with that, we close this session. Thank you again. Bye for now.
Thank you very much, George, Phil, and Yasjka. And after that, we'd like to take group photos. So please be online for a while.
Hello. Hello.
Thank you very much. We obtained a very good group photos. Thank you.
Thank you very much.
Thank you. Bye, everybody. See you soon.
Bye-bye.
Thank you. Yeah, thank you for coming. I appreciate it.
Thank you.
I'm from Agri.